Today it's Science Friday 47, and I asked my dad another question.
So let's get down to it. Well, welcome back to another Science Friday, this time again on a Saturday, but it's because it's as soon as I could get my sidekick here into the video. So he had another great question. Again, this school that he goes to, even though they're not really into science-type classes yet, just in their general studies classes, they do a lot of science. I'm very pleased with that. And they ask really, really good questions. As many of you are aware, I've been very critical of science curriculum in school, especially elementary school, for many years because I thought it was empty and unchallenging, and even a lot of the things that they said were just flat out wrong. But the education that he's getting in science in the third grade is actually pretty darn good. He comes home with great questions. So, buddy, what was the question that you came home with a few days ago?
Why is it getting colder up in the sky when you're getting closer to the sun?
That's a great, outstanding question. So, as you go up in the atmosphere, as many of you are aware, it gets colder, generally speaking, as you go up in the atmosphere. It's something called the lapse rate, and it's minus 5.5 degrees per 1,000 feet in the troposphere, which is the layer of the atmosphere that we all live in and everything we consider weather occurs in. So as you move up in the troposphere, the lowest level of the Earth's atmosphere, it does indeed get colder as you go higher, generally speaking. Not always, but generally speaking. So why is it that you get colder when you're actually getting closer to the sun? Well, if you get high enough in the atmosphere, the answer is it actually gets hotter because you are indeed getting closer to the sun, or at least that's part of it. But it wouldn't necessarily feel hot. That's what we want to talk about today. So today we're going to talk about the structure of the atmosphere when you profile it by temperature, the temperature characteristics within that layer of atmosphere. Now, there's several different ways to profile the atmosphere. You can talk about thermal properties, you can talk about electrical properties. Today, we're just going to talk about thermal properties. And when you talk about the atmosphere, in terms of thermal properties, there are 4 layers of the atmosphere. Now, starting at the ground, you get the troposphere. And once again, the troposphere is the layer in which everything that we consider weather exists, with a few very minute exceptions. It's where we live. The tallest mountains don't penetrate the top of the troposphere. So the troposphere is the layer of atmosphere that's closest to the Earth. Now, how thick is it? Well, it depends on where you're at. The troposphere is thickest around the Earth's equatorial belt, and it's thinnest up around the poles. And that goes for all layers of the Earth's atmosphere. Basically, the troposphere goes up to about 30 to 35,000 feet, somewhere in there. Then you hit something called the tropopause. And the tropopause is very important when it comes to steering storms that move across continental masses and move across the oceans, because the troposphere contains jet streams, and that's what steers storms. It's very important in terms of weather, but we're not really talking about weather today, so we'll revisit that at another time. Above the tropopause, there's something called the stratosphere. And the stratosphere and the troposphere vary by temperature profile. In the troposphere, temperature does indeed go down. And again, it's about 5.5 degrees Fahrenheit decline per every 1,000 feet, which means that warm air is buoyant, right? Warm air is less dense than cold air. And as you go up, as the air gets colder, the buoyancy increases. And that's why when the sun heats the ground and the ground heats the air above the sun, the water vapor in that air starts to condense. That particle, that bubble of hot air will rise in the troposphere because the atmosphere around it is denser than the air itself, which is heated. Warm air is less dense than cold air, so it's buoyant. It floats. And the higher it floats, the colder the air gets. Now, that air mass will lose a little bit of heat itself as it rises. But sometimes the buoyancy increases, and that's what creates thunderstorms. But again, that's a topic for another day. Now, the thing about the stratosphere is that's completely different. In the stratosphere, the temperature doesn't go down as you go up. For a long ways, it's kind of static. Then it actually starts to increase as you go up. So in the stratosphere, warm air is no longer buoyant, which is why clouds very rarely penetrate the tropopause into the stratosphere. They can do it, but the only reason they will do it is because the updrafts in the clouds are so intense that momentum just carries some of the particles through the tropopause up into the stratosphere. But if you go out on a summer day when there's thunderstorms around, and you look at the top of those cumulonimbus clouds, they're flat in the top. That flatness is where they've hit the tropopause, and they're starting to spread out horizontally. Because the tropopause and above it, the stratosphere, limit the growth of clouds because the temperature profile inverts. Now, the troposphere and the stratosphere account for about 99% of the Earth's atmosphere by mass. Once you get above that, and by the way, the stratosphere is where most of the ozone exists. It exists in the upper part of the stratosphere up near something called the stratopause, which is the top of the stratosphere. Once you get in above the stratosphere and the stratopause, you get into the mesosphere. And the mesosphere is again characterized by a negative lapse rate. So the temperature goes down with increasing height in the mesosphere. At the top of the mesosphere, there's something called the mesopause. And above the mesopause, there's something called the thermosphere. Now, the thermosphere just gradually doesn't have a well-defined upper boundary because it just gradually thins out as you move into space. But the upper part of the thermosphere is often called the exosphere. Now, here's the deal. This is the answer to MJ's question. It turns out, by temperature profile, the hottest part of the atmosphere is actually the thermosphere. In fact, the thermosphere is so hot that a lot of the particles that exist there exist in a plasma state. They're sufficiently energetic due to heating by the sun and some other things that they've actually managed to ionize themselves. The electrons around the nuclei have been stripped off, and you have an ion running around. That's a plasma state. You've got positively charged ions and then a bunch of electrons that aren't necessarily associated with any single ion. The reason for that's very high temperature. But if you went up into the thermosphere and you were on the shady side of the planet, you weren't in the direct sun, you wouldn't feel very much heat. You wouldn't feel warm at all. In fact, you'd feel very cold. And here's why. In our universe, heat always flows from hot objects to cold objects. That's a fundamental tenet of thermodynamics. Heat always flows one way, from hot to cold. And there's only 3 ways that heat can get from something that's hot to something that's cold. So in our solar system, for the most part, the sun is responsible for heating everything. And the sun is responsible for heating the Earth, except for, as we discussed the last time, the interior of the Earth is still hot, partially, some of it's in situ heat that's left over from formation. Some of it is heat that's currently being generated due to the radioactive decay of heavy elements, things like uranium, thorium, things like that. So the inside of the Earth does produce some heat on its own, but overwhelmingly it's a small amount compared to the amount of energy we get from the sun. Tiny percentage. So everything on the Earth, for all intents and purposes, is heated by the sun. Well, how does that heat get from the sun to the Earth? Well, there's only 3 ways that you can transmit heat in this universe: conduction, convection, and radiation. What did we say was a good example of conduction last night, son? If I heat... Go ahead.
Okay, so you said if you cranked like a stove up really hot and then you put a fork on top of it, it wouldn't get hot right away, but then it would eventually...
Right, if I touched it with a metal rod or a fork or something like that, or a metal knife, I would eventually feel the heat flow through that metal blade into my hand. That's because metals are typically very good conductors of both heat and electricity. By the way, that's for the same reason. And so gradually heat would be conducted from that stove into my hand. Now, do you have to touch the wood-burning stove in our living room for it to feel warm, or can you feel the warmth from it from a few feet away?
From a few feet away, because if you have boiling water and you put your hand above it, you can feel the heat.
That's right. And that's because there's 2 other things going on too. So not only is there conduction, there is some conduction that occurs, and the heat is conducted a little bit into the floor underneath the stove. But the main thing about that wood-burning stove is it uses convection and radiation to heat the room, which is why you don't have to touch it to feel the heat. The radiation is just the infrared rays that the stove is beaming out. The stove's hot, it's painted black, it acts somewhat like something called a black body, and it produces a very strong infrared heat signature. That's radiation. So that wood-burning stove is heating the room via radiation. The sun does the same thing to the Earth, except that radiation's in the visible portion of the spectrum. You can see it. It peaks at yellow-green right at around 530 nanometers. Well, convection is the last mechanism of heat transfer, and convection is what happens in a pot of boiling water. In that pot of boiling water, you have particles that move around. So the bottom of the pot gets hot, It heats up the water at the bottom. That water becomes a little bit less dense because it's being vigorously heated, and it'll start to rise. It experiences buoyancy, rises to the top of the pot. The cooler, heavier water starts to sink down, and you get that roiling motion. And convection can occur in any kind of a liquid or a gas, okay? Those are both called fluids collectively. And our atmosphere functions like a gigantic fluid. So when heat from the sun gets to the Earth's atmosphere, most of it goes straight through the atmosphere on the way to the Earth's surface. It heats the Earth's surface, and the Earth's surface is actually what heats the atmosphere. And it does it by all three mechanisms. It does it weakly by conduction. There's some conduction from the surface of the Earth on a warm day directly into something called the boundary layer, which is a layer of air that's closest to the ground. Now, once you heat up that air in the boundary layer, it starts to rise and it starts to circulate, and it spreads heat through the atmosphere via convection. And there's also some radiation. The Earth functions somewhat like a black body. It radiates some infrared heat back into space. That infrared heat is absorbed by things like water vapor and carbon dioxide in the atmosphere. That's one of the things that's responsible for global temperature starting to increase. We produced a lot of carbon dioxide, put it in the atmosphere. That's a so-called greenhouse gas. Yes.
And carbon dioxide comes out of our mouth after.
You do. When you exhale, you're exhaling carbon dioxide. What is it that ingests carbon dioxide and puts out oxygen? Plants? Yeah. So plants are good, right? Trees take in carbon dioxide, they absorb it from the atmosphere and produce oxygen. So there's a symbiosis between us and plant life on the planet in this carbon dioxide oxygen exchange. So the atmosphere is warmed by all three mechanisms: conduction, convection, and radiation. So when you get up into the thermosphere, it turns out those particles, those little gas molecules that are running around up there, are quite vigorously heated. They're very hot because they're being heated from above and below, and actually even more effectively from above in some cases. So they're zipping around. They're quite hot. But you know what? The pressure's really low. There's not very many of them. Now, so how is it that you're going to get heat from those few small particles into something as big as you? Well, it doesn't matter how hot an individual particle is. It's so small, its thermal mass is so small, that it can only impart a certain amount of heat to you when you come in contact with it. That's why in most cases, if you heat up a lot of gases into a plasma state, you could run your hand right through that plasma and suffer no damage, because there's so few molecules compared to the number of molecules in your hands, or atoms if you want to talk about it that way, that what happens is your hand is so great of a thermal mass compared to the thermal mass of those particles that you just poison the plasma. You instantly cool it down because your hand would easily be able to absorb all that heat. And that's what's going on in the upper atmosphere. Yeah, you have a lot of these particles, these gas particles that are in a plasma state, but there's so few of them that when they would impact you or your spacesuit or your spacecraft, whatever it is, they're just not able to transfer that much heat because there's only so much heat they can hold. So if you're in the shade, you would still feel really cold, even though you're way up in the thermosphere. Does that make sense?
Yeah.
Okay. So a few more things about the atmosphere, and then we're going to wrap it up today. So what is the atmosphere composed of in terms of elements? Well, overwhelmingly, about 78% of the atmosphere is N2. It's diatomic nitrogen, nitrogen gas. And about 21% is oxygen. Then the remaining 1%, there's some carbon dioxide, some inert gases, things like that. And those are in relatively fixed amounts. So that ratio doesn't change very much except over incredibly long time scales. We're talking billions of years or millions. We're talking millions of years, hundreds of millions of years for those ratios to change very much. Now, there are some gases that have variable concentration in the atmosphere. And those are water vapor, ozone, and a lot of nitrogen and sulfur compounds. Not diatomic nitrogen, but nitrogen and sulfur compounds. And they change over time in time scales that you could easily measure in a lifetime. There's also some solid and liquid particulates. There's some dust, water droplets, ice crystals. There are a lot of dust particles play an important role in the atmosphere because in some ways they shield the Earth from sunlight that's coming to the surface of the Earth, and they also provide condensation nuclei for snowflakes to form. And that's important in terms of precipitation. We'll talk all about that down the road. But anyway, I hope that answers the question. You know a little bit now about the atmosphere in terms of its thermal properties and why, indeed, even though it's counterintuitive, the higher up you go in the atmosphere, the warmer it actually gets. The warmest layers of the atmosphere are where the atmosphere starts to taper off in outer space. Now, one other thing before I get going is I mentioned that in the troposphere, most of the time it gets colder as you go up. But that's not always the case. Any of you that live in a mountain town like I do in the West, where there's a valley surrounded by mountains, will be familiar with something known as a temperature inversion. Those occur in the wintertime. Cold air turns out to be really dense. So if you get a big layer of super cold air that settles in over a mountain valley, it'll sink because it's a lot heavier than the warm air, and it will displace the warmer air. So in the morning sometime, we live about 1,000 feet above the valley floor here. When we get in the truck and drive down into town, we can watch the thermometer actually fall. I've recorded as much as a 20-degree drop as we drove down into town on a really clear winter day, because it's actually getting colder. You're driving down into a layer of cold air. That's known as an inversion. And the thing that sucks about inversions is, it tends to trap air in those valleys because nothing can move. You got this big, dense mass of cold air that's sitting in the valley, and it doesn't want to move. And it's going to take a lot of heat or a lot of wind to move that stuff out. So you can get in the West days and weeks sometimes where you get these high pressure systems that settle over the Intermountain West, and you get inversion conditions, and it kind of traps particulates too. So anybody that's running a wood burning stove, the smoke doesn't go very far away. It kind of stays in that inversion layer a little bit. The atmosphere is just absolutely fascinating. It was one of my favorite things to teach and to talk about. I taught meteorology for the whole time I was in college, and I love it. So we're going to talk a little bit more about that as time goes on. But anyway, that's it for this week. Thanks for the question, bud.
You're welcome.
No paywall again this week, and what do we say at the end of all these things? We'll be seeing ya.
Yeah.
Cheers.
Cheers.